a Santa Maria de Santiago desde quando?
2013.
2013, tá. Eu vou adicionar isso aqui. Eu tenho a introduzir você. Vamos, acho que a gente pode... bom, a gente vai fazer a apresentação em inglês, certo, Pedro?
Como você quiser, digamos.
Tá. I will switch to English then. So it's a pleasure to have Professor Pedro Orellana to talk to us today. Professor Orellana got his bachelor's at Universidad Católica de Chile in 1989. He got his master's and his PhD at Católica de Chile too in 91 and 94 respectively. He did a postdoc in Brazil at CBPF, Centro Brasileiro de Pesquisas Físicas, in 1995. And another postdoc at the Universidad Santiago de Chile in 1996. And since 2013, is at Universidad Santa Maria in Santiago. And today, Professor Orellana is going to talk to us about Andreev reflections and Majorana Zero modes in quantum dots and quantum rings, coupled to normal and topological superconductors. So, Professor Orellana, it's a pleasure to have you here today. Thank you very much for accepting the invitation to talk to us, and I pass the microphone to you.
Okay, thank you, George. Thank you for the invitation. I talk about Andreev reflection and Majorana Zero modes in quantum dot and quantum rings. The outline of this talk, I give an introduction about the Andreev reflection, Majorana Zero mode, some topics in Josephson currents, and give some results about our investigation in decay Andreev effect in quantum dots and the influence of Majorana Zero mode on Josephson and Persons current in quantum rings. Okay, and finish my talk with some conclusions. First, I introduced the idea of the Andreev reflection. When we have a system with a normal contact, a conductors and a superconductor. For example, here we have a normal contact, quantum dots, a superconductor. The quantum dot is represented by a single level. When we have an electron go from the left to the right, then the electron want to enter in the region of the superconductor, but if in the superconductor we have the gap, the superconductor gap, the single excitation is not allowed to enter in here, because here is only possible to obtain two Cooper pair, and instead it's possible to the electron goes to the for tunneling for in the region entered the region the superconductor, forming a Cooper pair. But for if this process is possible, if the hole is reflected in this region, and this effect received the name of Andreev reflection, and this effect was predicted by Andreev in 1974, and this effect now is possible to measure in system in nanostructure, and also is possible to obtain a spin resolved Andreev level. Yeah? Here we have the Andreev level produced by the electron and the hole in the nanostructure coupling to a normal superconductor. And in this system, measure the differential conductance and the different conductance. When we have Andreev reflection, the red regions represents the Andreev reflection in the system. Here we have the different voltage in the applied voltage in this system as a function of the magnetic fields. Okay, another effect is produced in this system. Is produced when we have two superconductors with different phase and a Cooper pair tunneling through an insulator. And then when we have a tunneling through the insulator, we have a supercurrent produced in the superconductor. And this effect was predicted by Josephson in this paper, called as possibly new effect in superconductivity tunneling, published in Physics Letters in 1972. And with this prediction, Josephson wins the Nobel Prize. And this effect is measured, for example, in quantum dots between two superconductors. The setup is here. Here we have the nanowire between two normal superconductors, and Josephson current goes through the nanowire between the superconductor. And this effect now is possible to apply, for example, in a junction laser using these Josephson junctions. Another topic relevant now in superconductivity is related with the Majorana fermions. Yeah? In 1998, Frank Wilczek wrote this article called as Majorana returns. Why Majorana returns? This is because Majorana was missing in 1988 in a travel between Naples and Sicilia. Majorana was missing, and the physics contribution of the Majorana also missing. But when Wilczek write this article, the contribution of Majorana began to be relevant in high energy physics and in condensed matter. What are the Majorana fermions? For example, the Dirac equation model the relativistic particle. Entonces, it's the wave function for the relativistic particle, for the relativistic fermions. And with this equation, Dirac predicted that a particle has a own antiparticle. For example, the electron has the positron as the antiparticle. And Majorana write a similar equation, but with a real solution. In a real solution, this wave equation, this relativistic wave equation, predicted a particle has their own antiparticle. Okay, but candidates for the particle has as antiparticle, for example, is the neutrinos. The neutrinos it's possible that are the Majorana fermions, and it's possible to measure the neutrinos are Majorana fermions with measure the beta double decay without neutrons. Normal beta decay is when a neutron decay in a protons and electrons and neutrino electron. Okay, and a double beta decays, then a neutrino decay in proton, electron, another neutrino electron. And if the neutrino is a Majorana fermion, the neutrino annihilate between them and produce a beta double decay without neutrinos. But this process is not measured at now. And in condensed matter physics, it's possible to obtain not precisely a Majorana fermion, but a Majorana zero modes. And in 91, Kitayev in a model, in a simple method with the nanowire, a quantum wire on the surface a three-dimensional superconductor, predict the formation of the two localized states produced by the topology of the system, and this bond state has the characteristic of the Majorana zero modes. And in this system, this model is possible to realize in a S-wave superconductor and a semiconductor on in the surface of the superconductor with apply magnetic fields, and with a semiconductor made with a material with a strong rise-by interaction.
3 cursos 6. Mas são poucos alunos. Por aqui, eles são assim, poucos alunos.
Okay. So then it's possible to obtain two bond states, and the two bond states in a nanowire are the Majorana bond state, okay, or Majorana zero modes. And this effects, this Majorana zero mode or signature of the Majorana zero mode was obtained for first time for the group of the Cohen in 1912, and they measured the differential conductance through the nanowire. Here we have the different conductance as a function of the applied voltage and the magnetic fields. And if you look at zero bias, we can see a signal of in the different conductance as a function of the magnetic field. For sufficiently large magnetic field, the authors find a signature of the Majorana zero modes for zero bias, and this claims that this signature are signature of the Majorana zero mode. And after this, several groups obtained a signature of the Majorana zero modes in the at zero bias. Okay? But this signature is not concluded. For the to affirm to the Majorana zero mode are present in the system. But in this year, a group of the Microsoft quantum team reports the observation of the topological gap in this system with two Majorana Zero modes in the ends of the nanowires. Here we have the region, we have the energy, and in the ends of the nanowires, the team observed two excitation relate with the Majorana Zero modes, and they report a protocol to identify a topological superconducting phase for this system. And this is the first time with a complete protocol to identify to a topological superconducting phase. Okay. Another relevant system for the observation of the Majorana Zero mode was predicted by the Liu and Berenger in 2012, excuse me, and they predict detecting Majorana Zero mode using quantum dots. And the setup is here. We have two normal contacts, a quantum dots, and a nanowire with a strong spin orbit coupling. Yeah? And with a proximity effect, the quantum dot is coupling with the nanowire, and the information of the Majorana Zero mode are leaked in the quantum dot and measure the transport through quantum dot. Measure the current through quantum dot. Is possible to measure the information of the Majorana Zero mode in the nanowire. They predicted that in the quantum dot, the different conductance is the signature is produced as zero energy and then in zero bias, and the maximum of the conductance with in a nanowire with a large length, they predict the conductance is the half of the maximum of the quantum in the quantum limits. Okay, this setup was carried out by these authors, and this author measured the non-locality of the Majorana Zero mode in hybrid nanowires. Here we have the quantum dots, in a cartoon of the quantum dots. Here we have the nanowires, and they play with the coupling between the quantum dots and the nanowires. Yeah? This play with the coupling between the quantum dot and each Majorana Zero mode in the nanowire, and the coupling between the Majorana Zero mode in the nanowires. And depends on the coupling, the spectrum of the Majorana Zero modes change, and they measure. Here we have the system, the quantum dots here, the nanowire here, the superconductor is the region in blue, and different contacts here, and they measure the different conductance here as the magnetic field is increasing. When the magnetic field is increasing, a Majorana Zero mode is present as zero bias here, and this region is robust as under the change of the voltage in the nanowire. Okay. Okay, now I give some results of our investigation. First, I talk about the decay and finite Andreev reflection in a triple quantum dot system. Here we have the system with 3 quantum dots and a normal contacts and a BCS superconductor. Here, the superconductor is a normal superconductor, a BCS superconductor. And the coupling between the quantum dot and the superconductor, I call it as gamma S. Here, the coupling between the central quantum dot and the normal contact is gamma N. And the coupling between the quantum dots are T12 and T32. Okay. And what is the decay effects? Decay effects in a atomic system is when when we have the spontaneous radiation or the excited atom in presence of the another atoms, and the atoms are at distance r. And when this distance is much smaller than the radiation length, the two atoms interact indirectly through the electromagnetic fields. And when these atoms interact through the electromagnetic fields, the spectral intensity has two signals. A white signal relate with the so-called super radiant state. We have a white width, and another with a sharp form and a sharp peak relate with the so-called super radiant state. Then we have a super radiant state and a super radiant state. And this is produced by the indirect interaction between the atoms through a common bath. The common bath here is the electromagnetic fields. And here the analogy is here. This quantum dot, the 3 quantum dots, for example, the up quantum dot and the down quantum dot, here quantum dot 1 and quantum dot 3 interact indirectly between the common quantum dot. The common quantum dot here is the central quantum dot. And this quantum dot and this quantum dot interact between through the central quantum dot. This is the analogy. And in this analogy, we have also analogy states. Yeah. Then for in a non-interacting system, when without the electron-electron interaction in the quantum dots, we have this transmission spectrum. Here we have the different conductance as relate with the transmission spectrum. We have this form of the transmission, essentially. Here we have the Andreev peaks, and in the region, in the center, around the zero bias, we have this peak. And this peak is related with the subradiant state in the decay effects. Yeah? And the white anti-resonance is related with the super radiant state in the decay effects. Okay? And relate with this, appear the so-called Andreev reflection. The central peak is splitting with the coupling with between the central quantum dot and the superconductor is increased. Here we have a half, one half, and two. When this coupling is increasing, began to appear these two signals, and the two signals are related with the so-called Andreev reflection. Okay. Here is the scale of the here gamma 10 minus 1. Here we have gamma 10 minus 4. Here is a sum of these regions. Okay, what happens when we consider the interaction between the electron interaction in each quantum dot and in the regime of the Coulomb blockade regime. In the Coulomb blockade regime, when we consider the Coulomb interaction, appear the normal spectrum is split in a spectrum for energy 0 and energy 0 plus U. Okay. Then here we have the gate potential in the quantum dots, and the right is the scale for the conductance. Here we have the linear conductance as a function of the gate potential, and in the right you have the occupation number. Essentially, is the charge in each quantum dot. And we can see that in the when the coupling between each quantum dot is weak, the coupling between the quantum dot is weak, then appear sharp states in the quantum dots relate with the supraradial state. And when this happens, the charge in the quantum dots for the states in each quantum dot is a single occupation. We have this form of the occupation number increase to a half of the occupation, and we arrive to the gate potential coincide with the value of U in each quantum dot. Appear the next value for the increase the charge in the quantum dots, and the charge in the lateral quantum dots increase abruptly, and the charge in the central quantum dot increase smoothly. Okay?
May I ask a question?
Yes.
Quick one. The conductance is for E square over H because it's a superconducting current, right?
Yes. Here we have for the Andreev the current in this case. The conductor is the Andreev reflection. For the numbers, here we have 4 A squared divided by H.
Okay, thank you.
Thank you. And here we have now the density of state in the global density of state is is the sum of the density of state quantum dot 1, 2, and 3. Okay, and this density of state, we can see the forms, the characteristic forms of the decay effects here for the when the superconductor is the coupling with the superconductor is zero. Only we have normal states in the quantum dots. And here we have the signal of the peak in energy zero and energy zero mass U, the normal peak and the Coulomb blockade peak. Okay, when the coupling with the superconductor is increased, a signal relay with the superconductor appear with a splitting of the first splitting of the superradiant state, and then also a splitting of the supraradiant states. Okay, and this splitting also occur in the Coulomb blockade states. Okay. Okay. This is for the interacting system. Okay. This here we have details of the density of state for energy zero here for different coupling with the superconductor, and we can see the Andreev states in the quantum dots. Okay, and in the Coulomb blockade peaks, this splitting is the split in the right region is missing. Only appear in the left region in this case. We think this is because we lost some symmetry for when the electron interaction is applied or is considered. Okay. Here we have now the different conductance for the system. Here's the Andreev conductance through the superconductor, and we have the forms of the different conductance for the two contributions for the different conductance. The contribution of the superradiant state, which contributes as fan of resonance as around zero bias, and a superradiant state that contributes as a superradiant state with a sharp resonance at the zero bias. Okay? And the sharp resonance zero bias also has the information of the Andreev reflection. Here we have the splitting of the Andreev reflection because we have a supercurrent through the superconductors. Okay, and we can model the form of the different conductance, as the different conductance have essentially three mechanisms here. One mechanism is the fan effect. When electron coming from the left, the normal contacts, goes in the region, it's possible to go produce a fan effect when the electron enter and out of the region of the quantum dots, and this produce a phase in the electron, and the different phase between the electron that enter and out of the range of the superconductor, the quantum dots, and the electron that go directly through the central quantum dot produce the fan effect. And fan effect is related with the super radiant states. And another mechanism is the another mechanism is the coupling between the quantum dot. In this mechanism, the quantum dot is effective in effective forms. The quantum dot are two quantum dot in series, and two quantum dot in series. The profiles of the conductance is a maximum in this case. And another mechanism is the because the quantum dot are interact. This quantum dot and this quantum dot interact through the central quantum dot, and the Fermi mechanism produce a Fano profiles. Here we have a Fano profiles for the Fermi mechanism, another Fano profile for the second mechanism. Okay, and this here is essentially a break beginner profile, and this the sum of the three mechanisms goes to the profiles of the different conductance when we have the three quantum dots coupling between the normal and superconductor contacts. Okay. Okay. This is the first part of the results, and another relevant influence of the superconductor is possible to when we have here a rings with a finite number of the quantum dots. Here we have a rings with a flux through the rings, and two topological superconductor nanowires with the two Majorana Zero modes. Here we have one eta 1, eta 2, the Majorana Zero mode in the left. Here we have eta 3 and eta 4, the Majorana Zero mode in the right nanowire. And these nanowires are coupling between the quantum ring through the lambda coupling. Yeah, and each nanowire in each topological superconductor nanowire are modeled through the Kitaev model, and in the Kitaev model, here we have the Majorana Zero modes. Okay, and we study here the Josephson and the persistent current. The Josephson current are the current between the two superconductors. Yeah, here we have a current in the superconductor, and the current between the two superconductors are in this case is the Josephson current. And when we have a quantum ring, also we can obtain a persistent current. The persistent current is produced by the presence of the quantum flux through the quantum ring. The quantum flux, the magnetic fields break the time reversal symmetry, and a current is produced in the quantum rings. And we in this article we studied the influence of the Majorana Zero modes in this current, in the Josephson current and in the Persington current. And first we studied the spectrum in the rings in the presence of the Majorana Zero modes and in the presence of the magnetic flux. Here we have the spectrum in the quantum rings as the magnetic flux, and here we have the spectrum as a function of the phase between the two superconductors. Okay, and we learned about the Josephson current and the persistent current. The persistent current is possible to obtain the persistent current as the derivative of the spectrum as the magnetic flux. And the Josephson current, we can obtain the Josephson current as the derivative of the spectrum in the difference phase. Okay, here we have and this example is for n equal 4, and the coupling between the superconductor and the quantum dot is for j equal 1. Okay. Here we have another possibility of the spectrum in the quantum rings for different coupling. In this case, for lambda equal lambda 1 equal half, and lambda 2 0, and lambda prime equal 0.3 without the coupling between this Majorana Zero modes. Okay, if the persistent current and the Josephson current are the derivative of the spectrum as the magnetic flux and the different phase, then we obtain the current. Here we have the persistent current as the magnetic flux, and we can see a signal, the signal of the Majorana Zero modes on the current, on the persistent current. For example, in the normal, if we have zero different phase in normal without magnetic flux, we have zero current, zero persistent current. But if you have a magnetic flux, we can obtain a finite signal of the Josephson current without different phase between the superconductor. In reverse, we also can obtain a finite persistent current without magnetic flux. Here, excuse me. Here, okay. For example, aquí is not clear, but we can obtain a finite persistent current in absence of the magnetic flux, but with the coupling between the two superconductors. Okay. here we have the persistent current. Here the colors, the scale of colors for the persistent current and the Josephson current. And we can see there is a signal, of the persistent current in absence of the magnetic flux. Okay. In reverse, also we obtain a signal of the Josephson current in absence of the difference of the phase in the superconductor. Okay. As the last results for our investigation, also we study the manipulations of Majorana bond state in the proximity of the quantum ring with Rashba coupling. Now, in this case, we have only a nanowire, a superconductor nanowire here with two Majorana Zero modes, and in the quantum ring, we consider also a Rashba coupling between the quantum dot. And in the presence of the Rashba coupling between the quantum dot, an additional current appears. We have normal current, normal charge current, and also we can obtain a spin current around the quantum rings. Okay? Here we have the spectrum of the system in the presence of the Rashba coupling. The Rashba coupling here is the coupling alpha, and without the Rashba coupling and with the Rashba coupling. Okay, and in the presence of the Rashba coupling, we have a signal in the current, in the persistent current, around zero flux. Around zero flux, we have a signal of the presence of the Majorana Zero mode on the persistent current, and this change of the current, the charge current, produce also a spin persistent current in the quantum rings. Okay. Here, in this case, we have n equal 4, and here we have in a number of the quantum dot in n equal 3. Okay. Well, in conclusion, based on the tuning of the magnetic flux and superconductor, we obtain the system of Andreev and Majorana spectrum for different size, observing zero energy crossing points and the flux bands, and also we obtain the Andreev reflection in the 3 quantum dots. In the 3 quantum dots, we obtain the decay effects related with the Andreev states, and in this case, we obtain the state with superradiant and supraradiant state. Okay, here this is part of our group. In pandemia, the form of work is this through the Zoom. Juan Pablo now is academic professor in the Universidad Antofagasta. Fabian finished his PhD with these works. Luis is a college. Ana Maria Calle was a PhD student. Now is teacher in Universidad Católica Norte. My college, Mónica, and Alejandro Gonzalez is a PhD student. Okay. Thank you. for the
Thank you. Thank you very much, Pedro, for this nice talk. This talk is open to questions now. I have a question regarding the, or maybe two questions regarding the. You presented many results, many different systems. The system with the 3 quantum dots. What technique did you use to solve the many-body problem?
In this case, we use the Harvard one approximation.
Harvard one, okay.
Yes, we consider the atomic limit first in the integral function for each quantum dot, and use the Dyson equation for include the contacts.
Okay, okay. And can we understand though that if you could go back to that slide you showed with the conductance, the 4e square over h conductance, that you had the discontinuities and the abrupt increase of the charge.
Okay. I understand. In this case, we have
the
linear conductance. Yes.
Yes. Can we understand that maybe in a simpler way, just saying that you have between you have quantum dot 1, 2, and 3, right? 2 is in the center. If you think about the bonding and the anti-bonding states of the quantum dots 1 and 3, the bonding state connects to quantum dot 2, and the anti-bonding state won't connect. So when you change the gate potential of all of them, this essentially zero width state is going to cross the Fermi level and it's going to be charged abruptly. Can we understand it this way?
Yeah, the system behave as is all in effective forms because the quantum dots are missing. The level of the quantum dot are missing through the central quantum dot.
Okay.
And missing produce the superradiant and superradiant state. Okay. Then this is the more important for understand the system. The spectrum of the system is separate between superradiant and subradiant. And the superradiant produces the anti-resonance in the conductance, and this superradiant state has a wide width in the resonance. Okay, and the supraradiant state has a very sharp form.
Zero width almost.
A coupling weakly with the contact, with the normal contact and the superconductor contact.
But can't we say that the superradiant is the bonding state, is the symmetric linear combination of 1 and 3?
The supraradiant state is the state in the center. In the center, and this state is coupling weakly to the continuum.
Okay. So it's not exactly what I am thinking.
Yes,
so it's a bit more complicated.
The coupling with the continuum, but with the coupling with if the system is asymmetrical, is strictly asymmetrical, then appear as a supraradiant state.
Okay. Let me see. We don't have Edson here. He always has a couple of questions. So apparently we don't have any more questions. You mentioned at the beginning the results of Copenhagen. but I'm not following. It's not my Majorana's is not my field of research, but I have been following here because Edson and some other colleagues are working on that. There was at the end of last year there were some. They retracted that paper, right?
Yes, the one paper published in the 2018,
2018, maybe.
Yes, was retracted by, in this case, is they claim obtain a plateau of for the quantum limits and for the Majorana Zero mode, but this plateau are much perfect, and the college of the Cohen, for example, Morik, Frolov, informed that these peaks in the conductance also can be produced by the normal Andreev reflection with disorder, and because this information, they retracted these papers, but now in the reports of the Microsoft, they claim they claim that the Majorana Bond state is real, and give a protocol to identify the topological superconductor phase. This preprint appeared in March. Now was submitted, I guess, in the Nature.
Okay, so it's not published yet.
No.
Okay. So let's see if we have any more questions. Apparently not. So we thank you again for this very nice talk. Thank you for accepting the invitation, and I hope it's not too cold there in Chile. What is the temperature there now?
No, now it's 70 degrees.
Is how much?
7.
7 is kind of cold. Yeah.
Now it's 10, I guess.
Okay. Well, it's winter after all.
Okay.
Okay. Okay. So, bye. Thank you very much, and I hope we talk again soon.
Okay. Bye.
Okay.
Ciao.
Bye. Ciao.